Hi, Assalamualaikum, and a very good day to all the viewers of this video presentation. This video is in purpose to present about my research project 1 CHE687, and the title for my research project is the effect of carbon dioxide gas towards the corrosion rate in wet gas pipelines. My name is Najmiddin binti Muhammad Jamal, a student of Bachelor's of Chemical Engineering from UiTM Shah, and my supervisor is Dr. Najmiddin Yaakob. Okay, so before I kickstart my presentation, this is the overview on what I'm going to present, starting from first the introduction, second part is literature review, methodology, and finally the conclusion. Moving on to the first topic, that is the introduction. Here I will explain more detail on my research background, objectives, problem statement, and scope. Okay, for research background, nearly for all of us, corrosion is best defined as the destruction or deterioration of a metal as a consequence of natural reaction with environment, and the product is often called as rust. And it is a curse that we have to bear with it helplessly. So the same goes to oil and gas world. So in oil and gas world, they have been facing the corrosion problem since the 1940s. And corrosion alone never fails to cause heap of dollars every year worldwide, as measured in equipments and maintenance, replacement, leaks, and also system failures. So these material degradation could result in the loss of mechanical properties like strength, ductility, and impact strength. So what is even worse is corrosion could also lead to loss of materials, reduction in thickness, and at times ultimate failure. So the crude oil and gas pipeline, in the course of being used for the purpose of transporting products, are exposed to various environments, specifically the offshore installations. Moreover, the lines could be buried, but in the long run, this exposure results in the liability to several forms of external and internal corrosion problems. So the process of corrosion takes place at all around the pipe wall. Thus, the corrosion in pipeline is separated to TLC, top of line corrosion, and BLC, bottom of line corrosion. Oil fields corrosion manifests itself in various forms of corrosions, among is which the carbon dioxide corrosion, or also known as sweet corrosion, and H2S corrosion, or as known as sour corrosion. There are two main objectives of conducting this research, which are, firstly is to determine the corrosion behavior of X65 carbon steel in carbon dioxide environment at various temperatures, and secondly is to characterize the surface morphology of the carbon steel exposed to carbon dioxide environment at various temperatures by using the optical microscope, and to analyze its splitting rate by using IFM. Moving on to the problem statement, almost any aqueous environment can endorse corrosion, which befalls under various complex conditions in oil and gas production, processing, and pipeline systems. Carbon dioxide gas is one of the co-corroding agents in the oil and gas production system industry, but it is to be noted that dry carbon dioxide gas is not itself corrosive at the temperature encountered within the oil and gas production system, but it is so the minute it dissolves in an aqueous phase, through which it can lead to an electrochemical reaction between steel and the contacting aqueous phase. So these serious consequences have become a leading problem worldwide. So the American Petroleum Institute, API, have designated different grades of carbon steel such as X52, X65, X70, X80 to pipelines, tanks, and oil rig construction because of its good corrosion resistance, high strength and toughness to withstand high operating pressures, field weldability, and low cost. But still, corrosion still continues to be a significant threat, as it can have a lot of potential implications for the safety, economic efficiency, and viability of structures. Hence, to overcome this problem, a study of corrosion behavior on X65 carbon steel in carbon dioxide environment at various temperatures were done in order to gain more understanding relating to this problem. Next is the scope of research, which I have divided it into three. So in this study, the corrosion testing experiment will be conducted for 7 days, and it will be executed ranging from 25 degrees Celsius to 80 degrees Celsius. And then the corrosion rate determination after the testing will be done through weight loss test according to ASTM G103 standard. Also, the metal coupon of API 5LX65 carbon steel will be analyzed its surface morphology by using SEM-IDS and its splitting rate by using IFM. Okay, moving on to the second topic, that is the literature review. So on this side, I have outline my literature review starting from oil and gas pipelines, pipelines corrosions, VLC-TLC, CO2 corrosion, field cases, and finally the research gaps. Okay, so in many regions of the world, heavy crude oil and natural gas must be transported through pipelines from the point of production to storage facilities or refineries. So basically in oil and gas industry, there are three most common pipelines. That is the first gathering pipelines, second is the transmission or transportation pipelines, and finally the third one is the distribution pipelines. So gathering pipelines involve in connecting the oil and gas pipelines starting from the wellhead to the processing facilities, while the transmission or transportation pipelines will deliver the oil and gas products to locations where they are used as fuels or where they are refined into useful product. Meanwhile, these distribution pipelines will deliver the products of oil and gas towards the end users. So this study will be focusing more on the gathering pipelines. So basically in oil and gas world, carbon steels are the most widely used pipeline material in petroleum and industries. Carbon steel material makes the pipelines great as it is prominent for its durability and strength. So basically, in other words, carbon steel is widely used as the constructional material in many industries due to its excellent mechanical and low cost. Okay, so what is a gathering pipeline? As I've mentioned earlier, gathering pipelines transport gases and liquids from the commodity source like rock formations located far below the drilling site to processing facilities, refinery or transmission pipelines. So in the past, most gathering pipelines were built in minimally populated areas, used smaller diameter pipelines that are operated at lower pressures and appeared to pose a much lower risk than for other types of pipelines. So as our nation continues to grow, our populations are spreading to these once rural locations, and an increased demand for natural resources means exploring alternate methods of producing raw materials that may come with some greater risk. Pipelines are currently still the safest means of transporting hazardous liquids and natural gas. So in every pipelines, there must be different fluid flow, where the most common flow regime in pipelines are usually stratified flow, plug or slug flow, and annular flow. So in stratified flow, the gas flows along the upper part of the horizontal pipe, whereas the liquid travels along the bottom with no significant interfacial waves. So this flow is gravity dominant and occurs at relatively low gas and liquid flow rates. As you can see in this figure, the flow has the simplest configuration of all the horizontal flow patterns and sometimes is referred to as stratified smooth flow. So for wavy flow, as the gas velocity increases in stratified flow, the shear forces of the gas flow over the liquid causes ripples on the gas-liquid interface, resulting in the formation of waves. So the waves climb up to the side of the pipe but usually do not touch the top side of the pipe wall, and then the liquid layer at the bottom of the channel starts to stretch thin, as you can see in this figure. So this flow is sometimes referred to as stratified wavy flow pattern. And then moving on to plug flow, the elongated gas bubbles in bullet shape and liquid plugs appear alternatively on top of the pipe. So basically, the diameter of the elongated bubbles are smaller than the tube diameter, which allows for a continuous liquid phase to appear on the bottom of the pipe. So this flow is sometimes referred to as elongated bubble flow pattern. And then for slug flow, with large amplitude wave or splashes of liquid, ultimately the waves build up and reach the upper wall of the pipe to form liquid slugs. These liquid slugs are then transported at the higher velocity of the gas, as you can see in the figure. So moving on to annular flow, this flow is momentum dominant and occurs at relatively high gas flow rates. As in this figure, the liquid forms a continuous film around the perimeter of the tube wall, and gas flows as a central core and entrains small droplets of liquid dispersed in the form of mist. Small bubbles gas may also be entrained in the liquid film. The thickness of liquid film is higher at the bottom of the pipe due to the gravity effect. Okay, so after the bulk fluid have wetted the surface of the pipeline based on the flow regime that I have explained earlier, this will after sometimes result in corrosions. Corrosions cost the oil and gas industry billions of dollars in loss of incomes and treatment costs every single year. Corrosion costs US industries alone an estimated of $170 billion a year, in which the oil and gas industry takes more than half of this cost. So according from research conducted by H.M. Shalaby, 33% of the failures that were analysed were attributed to corrosion. So this chart gives a comprehensive analysis on equipment failure in the oil and gas industry. And as we can see, the corrosion contributed to the highest 33%. This is then followed by other failures such as fatigue, mechanical damage or overload, brittle fracture, fabrication defects, welding defects, and others. So basically, the severity of corrosion is usually linked and dependent on factors such as water chemistry, protective scales formation at the steel surface slowing down the corrosion process, pH value, CO2 partial pressure increasing typically leads to an increase on corrosion, acid that leads to the decrease of pH value, temperature and flow velocity increasing, which can damage the protective scales form. As I have mentioned earlier, corrosion can be found at all parts of pipelines during its operational period, mainly internal and external corrosion. So what is internal and external corrosion? Internal corrosion is pipe wall loss or damage caused by a reaction between the inside pipe wall and the product being transported. So according from a research conducted by F. Ajayi, it is confirmed that internal corrosion contributed around 15% of onshore and up to 50% of the offshore pipelines failure, which makes it of a great concern to the oil and gas industry. Meanwhile, external corrosion is pipe wall loss or damage caused by a reaction between the inside pipe wall. So in other words, the external surface of oil and gas infrastructure is either exposed to the atmospheric above ground structure or underground that is buried in soil. So in this study, we will be focusing more on the internal corrosion. In order for corrosion to happen, it must be composed of three main core elements, which are oxidation, electrolyte, and reduction. So oxidation occurs at the anode side of the corroding metal, and while the electrolyte is the corrosive medium that enables the transfer of electrons from anode to the cathode side, and finally the reduction process takes place at the cathode side. So what happens is that when metal is exposed to a corrosive solution, which is the electrolyte, the metal atoms at the anode side will lose its electrons to form iron, and then these electrons are then absorbed by other metal atoms at the cathode side. So the cathode, which come in contact with the anode via the electrolyte, conducts this exchange in an attempt to balance their positive and negative charges. So the equation of the reaction are as stated besides. So moving on to the behavior of corrosions. For behavior of corrosion, corrosion in a pipeline can be observed either at the internal or external side of the pipeline wall. So internal corrosion in a pipeline take place at all around the pipe wall and can be simply classified into two categories based on their locations in the pipe, namely top of line corrosion (TLC) and bottom of line corrosion (BLC). So the orientations of each behavior are described by the o'clock position with respect to pipeline cross-section view. So TLC occurs typically at the 10 to 2 o'clock position of wet gas pipelines operated in stratified flow regimes at low velocity, when there is a difference between the external and internal conditions of the pipeline, leading to condensation of water vapor containing corrosive gases such as hydrogen sulfide, carbon dioxide, and organic acids. While for the bottom of line corrosion (BLC), bottom of line corrosion is the internal corrosion of different forms that occur from 4 to 8 o'clock positions of the pipelines, but the attention is mostly at the 6 o'clock positions. They are influenced by various factors such as temperature, partial pressure of carbon dioxide or hydrogen sulfide, solution of the pH, wall fluid shear stress, flow rate, and many more. So basically in this study, the focus will be more on bottom of line corrosion, that is BLC. Okay, so moving on, there will be two background of corrosion environment in pipeline depending on the primary organic acid present, which are sweet and sour corrosions. So what are sweet and sour corrosion? Sweet corrosion occurs with the presence of carbon dioxide, while sour corrosion happens with the presence of hydrogen sulfide. However, in this study, we will be focusing on the bottom of line corrosion in sweet environment. Okay, next, carbon steel CO2 corrosion, or as known as sweet corrosion, is a very common and a very serious difficulty in the oil and gas industry. It every so often results in the severe damage to pipes and equipment. Apart from controlling in the direct costs, which are associated with the loss of production and replacement or repair to the equipment damaged by corrosion, life and environmental safety must be protected with the thorough study of this type of corrosions. Carbon dioxide corrosion, or what's known as sweet corrosion, was studied since the 1940s in order to understand and control it. As we can see in this pie chart, according to Sridhar et al., as we can see, 28% of all oil field related failures are originated from CO2 corrosion. This was followed by H2S corrosion, corrosion at the well, pitting, erosion corrosion, galvanic, crevice impingement, and stress corrosion. So these failures befall primarily in areas to inadequate knowledge, lack of predictive capability, and poor resistance of carbon and low alloy steels to this type of corrosive attack. Okay, next, this is the water chemistry of sweet carbon dioxide corrosions. First, what happens is the carbon dioxide dissolves in water, and then it will be dehydrated in water to form carbonic acid. Carbonic acid is a weak diaprotic acid, so it will dissociate into two steps. That is, first, it will dissociate to form bicarbonate ion, and then it will dissociate again to form carbonate ion. Then this carbonate ion will react with the iron ion that comes from the oxidation step earlier, and then it will form a solid iron carbonate. CO2 corrosion is intensely dependent on the type of corrosion product film formed on the metal surface during the corrosion process. So the stability, protectiveness, and adherence of this film define the nature of the rate of corrosion. So a study by R. Barker has stated that there are two types of corrosion product film established on the metal surface. That is, the first is identified as the primary scale, which is porous, large in crystals, well adhered, and has black color characteristics. And the second one is the secondary film, is compact, small in crystals, non-porous, forms a uniform scale throughout the specimen surface, and is brown in colors. Many studies have pointed out that the main component of the film are iron carbonate and iron carbide. In flow system, corrosion films can observably grow for months without giving protection unless the steel is exposed to stagnant or wet conditions. So for the duration of a few days stagnation, corrosion products can accumulate on the steel surface and form protective films. Precipitation of iron carbonate on the surface of the metal decrease the corrosion rate by acting as the diffusion barrier for the corrosive species to travel to the metal surface by blocking a small number of areas on the steel surface and preventing electrochemical reactions from happening on the surface. While iron carbide is part of the original steel in the non-oxidized state that gathers on the surface after the preferential dissolution of ferrite ion. So iron carbide can be seen as the skeleton of the metal that is left over after the corrosion process has removed the rest of the metal. There are two forms of sweet carbon dioxide corrosion, which are first uniform corrosion and second is localized corrosion. Uniform corrosion involves in large area of corrosion at the pipeline wall, while localized corrosion involves in a small concentrated local areas. So there are varieties of localized corrosion, which are two of them are pitting and mesa attack. Pitting corrosion takes place with laminar flow and close to the dew point temperature in gas producing wells and form small holes, while mesa attack occurs in low velocities to medium velocities where the carbonate layer forms, however unstable to withstand the operating regime. While conducting this study, there are several research gaps that I have found out that limits the study of this research. So first, sweet or carbon dioxide corrosion has been a problem for the oil and gas industry for more than half a century, and substantial research has been invested to understand the corrosion mechanism and to improve the corrosion control, but still an unsolved issues, specifically concerning the understanding and control of corrosion remain. And then next, the determination of parameters and conditions controlling the initiation, propagation, and arrest of corrosion attacks is thus a topic of ongoing and future research. And then the roles on and properties of different parameters such as temperature in the carbon dioxide corrosion process also need to be further studied. Of particular interest is the high temperature parameters such as more than 100 degrees Celsius. Next, continued effort on critical parameter for corrosion as well as building corrosion database for verification and reference are necessary for providing the industry with adequate corrosion studies and further knowledge regarding the topic of corrosions. And then besides that, there are still not much studies related in bottom of line corrosion in comparison with top of line corrosion. Most of the studies that have been done are towards TLC. Thus, the behavior of corrosion, the corrosion rate mechanism specifically at high temperature at the bottom of line corrosion is then to be studied, and the ways of mitigate are also to be studied. So moving on to the methodology part, I will explain more detail on the procedures and methods when conducting these experiment studies, starting from the material and apparatus needed until the end of the general procedures. Okay, so these are the materials and equipment needed while conducting the experiment. The materials needed are carbon steel X65, hydrochloric acid, sodium chloride, antimony oxide, stainless chloride, and finally acetic acid. While for the equipment needed, we will need weight balance, optical microscope, IFM, and finally SEM EDX. Okay, so moving on to the general procedures, it involves 3 steps. That is first, material preparation, which involves the preparation of 2 X65 steel coupons, preparation of bottom solution, and glass cell setup. Second is the experiment part, which involves collecting data for temperature, pH, and observation of X65 steel coupons. And finally is the analysis phase, which involves corrosion rate analysis via weight loss method using UiTM G103 standard, and finally the surface morphology analysis via SEM EDX and pitting rate using IFM. For the preparations of 2 X65 carbon steel coupons in material preparation steps, the specimens used in this experiment is a pure carbon steel X65. So the preparation of the coupons is followed the UiTM G103 method, that is the standard practice for preparing, cleaning, and evaluation corrosion test specimens. So the coupons were polished using silicon carbide abrasive papers starting from 80, 120, 300, and 600 grade of silicon carbide abrasive papers to achieve the smooth surface of coupons. And then the polished coupons is further rinsed with water and acetone to remove polishing residual and possible grease. And then the X65 carbon steel coupons is kept dry and stored in a desiccator to prevent from any corrosion product to form on the coupons. And then for the preparation of the bottom solution is prepared by mixing 1000 ppm of sodium chloride and 500 ppm of acetic acid in a glass cell unit. Moving on to the experiment part, the data for temperature and pH need to be measured every day and tabulated in a table inside a logbook. So the coupon's temperature was measured every day by placing a thermocouple at the backside of the coupon sample, facing out from the glass cell lid. Apart from that, the pH of the water solution and the bottom solution were also to be measured to get a more specific data and result. Observations of X65 steel coupon surface, any formation of corrosion product on X65 steel coupon surface or any changes were needed to be visually observed throughout the experiment and also to be recorded. Finally, for the analysis part, the corrosion rate analysis via weight loss method by using UiTM G103 standard, the coupon was dismounted from the glass cell and washed in obedience with UiTM G103 method for weight loss measurement at the end of experiment. Both the precipitation rate, accumulation on rate of the corrosion product, and the corrosion rate of the steel of the mild steel sample was measured by the weight change method. Measurements were taken of the weight of the coupon prior to running the experiment and at the end of the experiment with FeCO3 scale present on the surface, and after the corrosion product was removed by using Clark solution. So the concentrations of Clark solutions are 1 liter of hydrochloric acid, 20 gram of antimony oxide, and 50 gram of stannous chloride. So from the weight loss measurement method, the corrosion rate can be calculated by using the equation of R equals to Kw over AT density. Okay, so finally, towards the end of the experiment, the samples retrieved from each test were examined at the end of each experiment by using SEM EDX and the pitting rate by using IFM. This is to investigate the morphologies of the corrosion product layers developed at the X65 carbon steel coupons. Before SEM, EDX and IFM analyzed, the samples need to be cleaned and in acetone to remove the surface contamination, dried and retained in a desiccator. Okay, so last but not least is the conclusion part. Okay, so to summarize everything up, in order to ensure a smooth and uninterrupted flow of oil and gas to the end users, it is vital for the field operators, pipeline engineers and designers to be corrosion aware, as the lines and their components fitting would undertake material degradations attributable to corrosions. There is an urgent need for preventing corrosion as it leads to a heap of dollars every single time. So this research aim is to determine the corrosion behavior of X65 carbon steel in carbon dioxide environment at various temperature. Apart from that, this research focuses more on the bottom of line corrosion, and it specifically studies on X65 carbon steel as the sole representative of the pipelines in the context of oil and gas industry. This research is based on the data obtained from various temperature of the carbon steel exposed to sweet environment, and then its weight afterwards are being calculated. So the corrosion rate was calculated and the data was analyzed under SEM EDX and IFM for its pitting to ensure the result obtained are precise. So I guess that is all for my presentation video, and I hope that whoever that is watching this will get an insight on this serious and famous topic. And I also would like to take this advantage to express my gratitude and thanks towards my supervisor, Dr. Najmiddin Yaakob, for the constant guidance throughout my research study. So thank you so much for watching, and bye.